So C, then Mohali equivalent one, I want this curve, fine, over Q bar. 2, subgroup 2 of index n. So this gamma 2 plays a key role in this whole discussion. So of course, gamma 2, everybody knows that this is the kernel of the map Z to S 0 and 3. So this n plays a key role. 3. Okay, sorry. That's that. 3. This is your boundary of X, and this plays a key role in the whole talk. And yeah, and there exists a n sheeted, the same n. Covering map. And inside this, we have this boundary. This will go to 3. Point here. Sorry? Yeah, sorry. No. Thanks. Yeah, thanks. H is our usual upper half plane. And there exists a bicolored graph with n edges. This n is same as this n starting with. This same as this n that is starting with. Okay, so with that, so design. Graph with certain ordering. Edges. This design is obtained. Let's give some name to it. Let's call it F. F is this covering space. Okay, so this colored 0 correspond to zero, and color 1, F inverse of 1. And this F inverse is 0, 1. These are the edges. And the most obvious things you can think about, examples, you can have if C, 5. So star of 0, 0. Okay, we can draw this, and similarly, if star of infinity, so you can draw this. So this is draw a different color. Yeah, so this. Okay, so with that, I define the main problem of this book. Vertex, each vertex, yes. Okay, so you have this x. I will define the main problem that we're interested. X is a curve defined over q bar. So you have this d naught of x in x and so inside this you have this p naught of x So this purview, I should like to use start with any curve, okay? Any curve defined over q bar. So this theorem says that there is going to be a subgroup gamma. So having said that, this is not effective. So if you have a given curve, it is not easy to write down the subgroup gamma. Okay. So the questions, that is the title of the talk, following for any curve. So I have defined this hospital subgroup. So the x equals to x. Yeah. Boundaries, all these points are boundary of x. I just take out the boundary of x. Yeah, boundary of x. So P naught of x, this is the hospital. Sorry? A priori, no, but this is, yeah. So this is hospital subgroup. And of course, you can recognize this. This is a subgroup of naught of x. The x's. Of course, if you take this x to be something of x, you will land inside pic naught of x. So the question is, for any curve x defined over q bar, can you give a criteria to determine if P of x containing pic naught of x torsion points of the pic naught. So this is what we call Manin-Drinfeld formula. And so this curve x is arbitrary curve. It can be any curve defined over q bar. And the questions I'm asking, this is Manin-Drinfeld question. So is it true that Cx is contained in pic naught of x star? Okay, so I would like to address these questions in this talk. So remark of why it is called Manin, it is for gamma naught of n, we take n equals to p naught p equals to pic naught of x naught p star, and this is a famous theorem due to measure. And well, this theorem is now being generalized for naught of n equals to naught of n. Or this is recent result due to Yo and Brain. Building on work of the several authors. Okay, so definition. Subgroup in gamma 2 to have Manin-Drinfeld property if order of this Cx gamma is finite. So this is I give a name to it, a subgroup gamma, subset of gamma 2 is said to have a Manin-Drinfeld property if this order of this cuspidal subgroup. So I have not defined this gamma, but you have this for every subgroup gamma of gamma 2. This theorem will tell you that there is going to be a curve defined over Q bar. And for that, you can define the cuspidal divisor group as in this theorem. And I asked that, can you give a criteria to determine when this cuspidal subgroup is finite? Okay, so of course, why it is called Manin-Drinfeld property, because for congruent subgroups, we do not realize this when you're working, but for congruent subgroups, we have a remarkable operators, Heike operators. And these Heike operators are there, and using this, all congruent subgroups as Manin-Drinfeld property. For the obvious reason that it has all the Heike operators, and using homology groups, so Manin and Drinfeld prove that this cuspidal subgroup is gamma. Okay, so you have these Heike operators. For that, maybe you think that this Manin-Drinfeld property is true, but as you know, this is there are several times in this conference. Farmer's curve is not a congruent subgroup. We have to go beyond congruent subgroups to get see that is it true that always these questions, the Cx is contained in X naught of X star or not. Okay, so the second example is it is already there in this conference, Farmer's curve. So it is of course given by equals to okay, so I will recast this curve in terms of this theorem, Bailey's theorem. Just now I erased. So there is a map gamma 2. Let me recall for you. So this group gamma 2 plays a key role in this whole thing, because you have this gamma 1 modular plus minus 1. This is generated by two nice matrix A and B, which is something special. A is given by 2, 0, 1, and B equals to so lower triangular. And you see this P pi 1 of P minus 3 point infinity. This is infinity, so this is A and B. Okay, and so this curve, Farmer's curve, correspond to you can make it explicit. You have this map identity. So I take this n to be odd. Where 0, and look at the kernel, and this map is A goes to 0 and B goes to, and this kernel is generated by A to the power n and B to the power n, and this Farmer's curve F and C is correspond to this gamma n in Bailey's theorem. Okay, so so it's a fact n not equals to so it's ABA. Right? Yeah. Okay, so if you take n not equals to, say most of the time I take this n odd, n not equals to 1, 2, 4, 8, this, you see, this gamma n is not a congruent subgroup. Okay, so it seems that okay for this is seems to be an examples where this Hecke operator will not work here, but however Rollick prove that gamma n has Manin-Drinfeld property. So you start to believe, okay, there is nothing special about the Hecke operator, but this Manin-Drinfeld property is always true. Okay. However, for most of the examples, this this Manin-Drinfeld property is not true. So I'll just give a proof. This is not a complete proof, and this is something related to the theme of this talk, theme of this conference. I mean, for general, I don't know that. Is it true? I just know this. I don't think it's a true. So even for modular curves also, this is pretty recent. This year is 2023. So beyond modular curves. Okay, so yes, suppose yeah, so I'll prove that this is a yeah, so gamma n, however, has this Manin-Drinfeld property, but you have to go beyond gamma n. Yeah, so what there is nothing meaning of this beyond gamma n, but there are some curves for which this Manin-Drinfeld property is not true, and the proof is the following. So this is the proof due to say this beautiful. This is okay. So you have this x that's inside Jacobian of x goes to x minus infinity. Yeah. So again, for general curve x, there is no meaning of this infinity, but this is a Q-rational point. So you have this by conjecture, which is a Reynolds theorem. You have this, let's call it I intersection is finite. Now you choose, okay, so this is, I mean, I'm trying to prove that this general X does not have, I mean, I call it MDP. Yeah, Manin-Drinfeld property. Okay, so yeah, so you have this IX intersection Jacobian of X is finite. So now you have to choose X so that quantity of X is big enough so if it is true, then this Reynolds theorem is false. False for this X. So you cannot have this Manin-Drinfeld property is true for all X. And soon, explicitly, the Gross and Rollick we found an example. Proved you have to take this curve X. So this is a quotient of Farman's curve b to the power p minus you take this curve and this is a quotient of the Farman's curve. So for which this for p, so this is Farman's curve of exponent p. Its property is not true. Sorry? Yeah, sure. Yeah. So after so yeah, so it's not always true. So we okay, so around the same time, Murthy Ramakrishnan constructed for any curve for any ring R, we can construct this HR R, and this is generated by of course by Z with X Z. This of course Z equals to XY. Okay, so so you have this HZ. This is similar to Farman's curve. I have this gamma 2, and I prefer to call it gamma n. And this map is A X Y and C. Yeah, C is this map. I should have defined it. Yeah. C goes to X, Y, X inverse, Y inverse. So C is inverse. Okay, the question they asked Murthy Ramakrishnan that does gamma n has Manin-Drinfeld property. Okay, so I will give a criteria to determine when this property is true. And the answer to this question is that for n equals to 3, this is gamma n, gamma 3 has this Manin-Drinfeld property, but n equals to 5. So this n is this n, and gamma 5 does not have Manin-Drinfeld property. And in general, we expect that they most likely it does not have Manin-Drinfeld property, but we don't know the proof. So maybe okay, so I will just give an answer to this question, the definition. So our answer is in terms of Eisenstein cycles. Cycle. So we whole work we use very specifically. This is a Riemann surface structure. We do not, if you do not have this Riemann structure surface structure or this gamma 2 structure, then our work this plays a very key role. This pi 1 of this you have only this generated by A and B, and this you have a covering map from this XC to P1C that plays a key role. Okay, so the Eisenstein cycle corresponding to divisor E is the unique element yeah, this is not an embedding map here. This map there is no, but this map it is. This is reduction modern map. Yeah, but there is a map from here to here. This map there is no. Yeah. Sorry. Your X and Y. Your Y. Yeah, okay. Fine. Yeah. So is it unique? Okay, that's okay. Yeah. Yeah. Okay. Okay, but then there is a commutator of this. Okay, so yeah, that's fine. I'll just stick. Ah, okay, okay, yeah, sure. This one is why? Yeah. Now there is same X, Y. Fine. Yeah. Okay, so the unique element is ED R such that boundary of ED and equation of ED to 0. So this is my definition of the Eisenstein element. This is the certain element of the homology group. Okay, and this second condition, this says that this is complement of the cusp forms, and this boundary this boundary should encapsulate this divisor D. Okay. Yeah. Okay. So you have this. So as I told you, this gamma 2 plays a key role in this talk. So if gamma 2 is generated by these two elements A and B, you have this, start with any divisor. So you 1 to R. So this P, so I call R, this is your support of D. So I D plus, this is D, A for support of D is contained in, you see the cusps, so these are the Bailey maps. So cusps, they are always lying over, sorry, this is 0 infinity. The cusps are always lying over 0, 1, and infinity. So I just break these cusps into the sub cusp lying over 0 and infinity, and the other set of cusps lying over 1. Okay. So D minus F of support of D containing 1. Okay, so for theorem, so theorem is roughly true. I just suppose support of D contained in D plus or D minus, then D is of finite order if and only a priori, these Eisenstein elements are in R. These coefficients are in R because there is a pairing from H naught of X by X to this H1s with coefficients in R. So I demand so that divisor D is of finite order if and only if these corresponding Eisenstein cycles, this belongs to this H1 of X. This is rationality statement. Okay, and this is this Eisenstein cycles. You can figure it out. These are in Q or not. Okay, that is going to determine this. You have these arbitrary divisors. You have this is Q rationals or not. This satisfy this Manin-Drinfeld property or not. Okay, corollary. So arbitrary divisor D equals to, you can write it as D1 plus D2. So then D is of finite order if D2 okay, so that if you start with, so this is not unique, by the way. So there is certain ambiguity there, but D is finite order if each one of them, this belongs to each one of this. So I stated it just for, in general, this statement is little more involved. So I just for exposition, I stated in this way. And we used crucially generalized Jacobian. So for every divisor, you see, we are interested, if you start with the divisor, the corresponding divisor is torsion in the pick not or not. And we heavily used not only this J naught of n, but you have to use generalized Jacobian. Yeah. Yeah. You have to make, yeah. You have to explicitly, you can make it another point, right? You add the divisor and then you desimplify it, right? Yeah. Yeah. So I'm not saying that, yeah. Yeah. Yeah, so we have to, so that's why our, if you look at our paper, we use generalized Jacobian to state it, okay? So this is for the, yeah. Okay, so, for every divisor, so D, you can look at this C, this C, this D, H1 of XZ. Yeah, so we, our actual statement is in terms of this generalized divisors. Yeah. Okay, so the advantage of this kind of statement is that we recover Manin-Drinfeld theorem because for congruence of groups, we actually computed, so we have been working on this for some time, and Loic Merrill started. So this ED, this is actually in H1 of X partial of XQ. So we recover Manin-Drinfeld theorem here. Remark. Okay, so I'll just put some remark here. So So congruence of groups ED belongs to H1 X of X Q. And I just put some remarks. So the advantage of our kind of criteria is that you see we are starting with starting point is a Bayes theorem, and Bayes theorem we are starting with a subgroup of gamma subset of gamma 2 of index n. So if you want to check this ED, it is only finitely. So we are interested in you have certain object with coefficients are R, and we are interested in if this rational or not. Even this Q bar is good enough, then you can do trace kind of argument to make it rational. Okay, so and Murthy Ramakrishnan, so this is the 1986 same paper. Krishnan gave a criteria in terms of Fourier coefficients of Eisenstein series. Well, you need to check all the Fourier coefficients of Eisenstein series to say that these Eisenstein cycles, these are these D is of finite order or not. But here in this case, only finitely many checkings are required. And Scholl also gave a criteria in terms of Eisenstein series. Eisenstein series. And recently, Claire Burin gave a criteria in terms of Ramanujan symbols. But again, you have to check for every gamma subset of SL2Z, you have to compute this each Ramanujan symbols and check the rationality. Okay, so I will just briefly, this is not a proof, but I'll give how we prove this. So proof of the theorem. So starting point is the work of Manin. But the way I did this is work of Merrill, because Manin worked with SL2Z and Loic Merrill started working with gamma 2 from his thesis. So we have this map gamma 2 one of X. The advantage of this Manin map is you have this G0. Okay, the advantage of this Manin map is that there is no Manin relations. So this map is an isomorphism. So compared to Manin's theorem, so if you're working with SL2Z, yes, there is a surjective map, but it has a kernel. Okay, and so but here, if you are working with gamma 2, this map is an isomorphism. And similarly, we can do it with interchanging D plus and D minus. Okay, and Z is an isomorphism. Yeah, sure. When you're taking gamma 2, there is a yeah. Okay, so so this map is an isomorphism. So Manin did it for SL2Z, but this is a kernel. But if you working with gamma 2, so this map is indeed there is without kernel. This is an isomorphism. Okay, so what you have, if you're working with, you want to study something in this group. Okay, so you start with this ED, you can write it as 2 if Vg. Okay, so the question boils down to checking if Vg belongs to Q or not. Okay, so just this is not complete proof. Okay, so proof of the okay, so we have a map, retraction map. R to each one of R. So this one is the C. You have this map R C equals to integration C of omega. So given a divisor E, you can always find such that boundary. So yeah, I did not define this boundary map, but boundary map is a map from this homology group, relative homology group to the cusps. Okay, so my claim is that so you have this CD, CD, and you have this H1. Right? Not 0. Exact 0. So the sequence is over R x 0 depend only if R x. So you have this delta of and D. So this is your the delta map is a linear map. So this is yeah, CD minus RCD. Yes, it's here. Yeah. Yeah. Question is rationality. Okay, so something is there, so this is a Q or not. Okay, so so that just implies that D, so that implies. Okay, so then we just go back to the book of Lang. He is a finite order. You can only by Lang's belongs to H1 of Q. That is, you can only ED. So this is roughly this is the idea. So now I'll just talk about this Heisenberg curve. Just I defined. So so Murthy Ramakrishnan defined Heisenberg curve the way we have defined, but we realized that this Heisenberg curve is a covering of Fermat's curve. Okay, so we just go back to the farmer's curve. So we have this P1C. C. This curve is given by x to the power n. Or n, and the map here is given by x to n. So it is of degree n square. So these are ramified, the ramification point. You see for a farmer's curve, so this is what the point is. So you are starting with the curves. So a priori, when you are defining for a subgroup, that is gamma, for a subgroup of SL2Z, this is your, you have this gamma modulo P1Q, that's a cast, but here, so this is given by polynomial equations. So you have to give ramified points only is going to give you the cast here. Okay, and the ramification points, this is all Rolex, this is AJ. A01 and A equals to A0. Okay, and divisor x minus j equals to Cj and 0 of y Aj Cj z minus epsilon zeta j. Okay, so we rewrite. So you have a divisor. Yeah, is this? So I choose this, you see, we're taking the summation over I from 0 to n minus 1. So I choose your representative. I n sorry. So I have this divisor dA AI, and similarly for, you see, there is certain symmetries with X, Y, Z and A, B, C that is there for farmer's curve. And similarly, we can define this. Similarly, we can define for DB and define similarly. Okay, so this is a theorem due to Rolik and value. Yes, sir. E is here. Yeah, so the class of dA is of order n. So I define this F A, this is your NZ I. Okay, and so dA n. So I have this farmer's curve is, you have this farmer's curve Fn 3, and this is of degree n, and this is, there exists an unique cyclic covering of degree n of Fermat's curve, and this is our Heisenberg curve. Okay, so this Heisenberg curve is the curve corresponding to the gamma upper n that I defined. Okay, and so and this is going to be the degree n covering of the Fermat's curve. Okay, this is our theorem. So okay, so I just, yeah, so I should rather call it Fn prime of C. Okay, so this theorem. Fn prime is defined over Q, and Fn prime corresponds to gamma n. Okay, in the last, yeah, so this is theorem, and in the last 5 minutes, I will talk about when this Fn, the question is when you have this Fn prime has this Manin-Drinfeld property connecting to the first part of the talk. And you feel like, so for whether this is a congruent subgroups or not, well, for n equals to 3, we wrote down the design, the drawing for this Fn prime. It turned out that this is a drawing with 9 vertices and 9 edges. And if this is gamma 3 is a congruent subgroup, so there is a old criteria due to Wolfert. Yeah, sorry, his name maybe, this is correct. Yeah, Wolfert, you have this gamma 6 contained in gamma 3, contained in gamma 2, but this index is 149. And this index is 27. So you cannot have. So this gamma upper 3 is not a congruent subgroup. Okay, and what we proved, okay, so this is a bare hand computation, not very. So gamma 3, so I will just state it in. Gamma 3 has Manin-Drinfeld property, but property. And roughly, the idea is that we computed the genus. Okay, so once you have this information of the curve, you can compute, amazingly, we can compute the genus of this F3 prime. And for F3 prime, it turns out that this is an elliptic curve. Okay, and because elliptic curves, and we can compute the J invariant also of these elliptic curves, because there is a subgroup of order 3 acting on this, because you have information about the quotient group. So that is going to give you information about the J invariant. It turned out that this J invariant is 0, and this is an elliptic curve. Gamma 3 is an elliptic curve. This is not approved. So gamma 3, so this F3 prime is an elliptic curve with J of F3 prime is 0. Okay. Unfortunately, for n equals to 5 onward, it's not an elliptic curve. And what you have, so but still we computed the genus of that, and it turned out that if this has Manin-Drinfeld property, so we use Kustal-Neveu-Savary kind of inequality that's going to give you a certain bound on the genus. but that is violating the genus that we computed for F5 prime. So if genus of F prime violates if the property is true for phi, then which is definitely not true. So this if phi prime has does not have Manin-Drinfeld. Okay. Thank you very much.
Are there any questions or comments?
When you define this P naught X, then you said that D belong to D naught and D is equal to DF. Right? When you define P naught X, you define.
Oh yeah, okay, fine. Yeah, first pillars of
D belong to D naught X and D is equal to DVF. Right?
yeah.
So do we need this condition that D belong to D naught X?
P naught X. Yeah. So this is subgroup of this, right?
Like we don't the degree of every division, principal divisor is always 0. Right?
Yeah, we need that. With what is the D naught of X when you define this degree 0 devices? If it is a pick naught of X, should start with a pick naught of X. That is your question, or what?
I'm saying like you have written D belong to D naught X and D is equal to divisor of F.
Yes.
So I'm saying that do we need this condition D belong to D naught X? Or like just saying D is equal to.
Yeah, degree 0, yeah. Yeah, we need it. Yeah, as long as supported false. Oh. You need to be something of D naught of X, that capital D.
Okay. And this using all congruent subgroups have this Manin-Drinfeld property. So what do you mean by is like all congruent subgroup for every label or like
every level, yeah.
There is like it's not like label something 2 or
no, because you have this certain nice Hecke operators are there. We don't realize when you realize work on that. These Hecke operators are too strong. And if you have this homology group, so there is all these Hecke operators acts on this, and that's make it any damage.
Oh, thank you.
So I have a question about your claim, the CD minus RD. I didn't understand the full statement you were. What is the claim? The claim was, then you said the sequence splits over R if and only if, which is same as delta X equal to 0.
Yeah, this sequence splits over R if and only if that. So this is like this linear basic algebra. But all of them are in the homology group, relative homology.
They're all in the relative homology.
Yeah,
that's what I was wondering where the.
This is a coefficient, a priori coefficients in R, but D is a finite order.
It splits over R. Is that what you were saying?
Because it's a vector space, right? Over this.
Yeah.
So this is vector space.
Okay.
Yeah, but this over Z there is a problem.
So then what's your then you wrote Rx equal to X or something. I mean, the usual criteria is that the Hodge structure splits.
Yeah.
Right? Yeah. This is the same thing as that?
Yeah. General for gamma 5. Yeah. So all the cast and all are 27 cast and all. Okay. Right. No. We just found that this is okay. So do you? Yeah, I completely had a computation. Yeah. So this is like a arithmetic surface. We are considering it an arithmetic surface. So we have this curve defined over this XZ, and then you have this curve over 11. We computed it. So C bar, this divisors here. So find the divisors here in this fibers over 11. And then this. Okay, we don't know the structure. Staffers. Hypertrophic. There's not a hypertrophic. Come up. Yeah, so it's 27, I think. Yeah, 27. No, yeah, so yeah, just. Yeah, just a minute, yeah. Yeah, so. Yeah. Yeah, so over say there is a curve over C5. Okay, so there it is genus. So we did not use for X comma, but definitely it's 125, right? You need to check it. Okay, something like S cube. Okay, so yeah. But it's big. Okay, it's not 2. Okay, so if this Castelnuovo-Savary is true, then it is like less than equals to 2, but it's big. Yeah, but we computed. We can compute genus of this F type. That's completely there. Yeah, and the first property, you can have this, we wrote down this actual design for this gamma 3. That is also possible. But for gamma 5, it's pretty big. Okay, 25 vertices and all. Yeah, 120.
Any other questions or comments? If not, let's thank Debargha again for a very nice talk.